If your mom asks you what you did in school today, and you want to say something really impressive, you can say, I did some subatomic chemistry. That's what we're going to do today. We're going to do some subatomic. It sounds super fancy. It's not actually that hard. I learned about the origins of subatomic chemistry. That's what you can say. Man, are they going to be impressed. All right. We will start by drawing an atom. Draw like your mental image of what an atom is. Okay, I bet if you guys say atom and draw a picture, you're going to come up with that classic Jimmy Neutron type thing that has a dot in the middle and some like loops around it like that. Smile and nod if you drew something like that in your notebook. Okay, that is a pretty good model of the atom. We're going to improve that as we go in these next couple weeks. But that is not John Dalton's model of the atom. Right, like Dalton's atom. Okay? John Dalton's model of the atom was this. Because he didn't have a nucleus or electrons. John Dalton's model of the atom was a solid sphere. Bloop. No parts. How the different atoms of different elements were different, he didn't know. Maybe they're like this. Or maybe they're spheres of different colors. Or maybe some of the spheres are oval. Like how, if this was what carbon was, like what nitrogen was, he knew it was sort of similar, but not exactly the same. This is where we are. Okay? This is our sort of ending point of last class. I think we also got to Ben Franklin and the kite, yes? And the fact that he had electricity, but he didn't really know what it was. That's kind of where we're in. We've got Dalton's model of the atom, the solid sphere, and we've got something about electricity. And now we're going to get this person. Okay? This person, guess a century that this person is working in. 1800s, 1900s is reasonable. He's wearing normal clothes. He doesn't have like pantaloons and long hair the way like Ben Franklin did. So we're not getting somewhat modern. This person happens to be named J.J. Thomson, and they're working in the 1890s. Maybe the Edwardian time period or late Victorian. I don't know. So J.J. Thomson. 1890s. You don't have to worry about the sixth part, just generally the 1890s. He's fairly modern. He's working with electrical experiments. And he's got these glass tubey things over here. These glass tubey things are also in this picture here. They are called cathode ray tubes. Okay. A cathode ray tube is a beam of electrons. And I want you to draw one into your notebook. It doesn't have to be perfect. I'm gonna draw a little like thing like that. Get a new color. Feel like beam of electrons. Beam of electrons. What is the person in the picture doing with the beam of electrons? Pointing it. What is he doing with it? Projecting it? So the beam is going this way, but then he's done what to the beam that should be going down the tube? Taking the fan? He has bent it. He has bent that beam of electrons. Instead of going straight down the tube, they are getting tweaked. And the beam is this like light colored part that is getting bent down. I'm going to move this out of the way so you can see that it's been bent. He's doing that with a magnet. Okay? In so doing, okay, they can see that this beam gets bent up towards the positive and away from the negative. What does that tell you about the charge on electrons if they're attracted to a positive and repelled from a negative? They're negative. And that is the first important improvement on Ben Franklin. We have, by bending electrons in a cathode ray tube, we prove that electrons, oops, let's get to a marker. Electrons are negative, indeed. Electrons are negative. They can also see that it doesn't take very much charge to bend them a lot. So not only do they now know electrons are negative, but also very low mass. Electrons are very light. The fact that you can take an electron and tweak it and bend it and throw it against a screen at a particular spot is useful in this device over here by Sam Taggart. This device is a television. Okay? Back in the day, televisions used to be deeper and a lot heavier than it used to be. But if you get yourself a socket set, you can just take this back part off of the TV and set it over here and reveal the inner workings of the TV. A lot of it's hollow. We got this thing right here. This right here, turn so you guys can see a little bit better. This right here is a cathode ray tube. Okay? But instead of just going out as one beam, it's got a lot of those positive plates. You're going to spread the electrons out and smear them across the screen. And when I turn this puppy on, okay, it's going to be loud and annoying. Okay? It's going to create an image by having a lot of dots hit different places on the screen. And if I press like the select button or the menu, I can get a bunch of stuff. This is an old TV that someone was throwing out in my neighborhood. These old shaped tube TVs shaped like this. But I'm going to take a magnet, the way that guy has the magnet, and the way like those positive plates create a magnetic field, and I'm going to move it around. Oops. One more time. I'm going to move it around back here. And those of you can see, the color is changing on the TV as I move it around. If I go way back here, I can totally move the image on the TV by moving this magnet around. Because that's what generates the image on the TV. Okay? Come on up here. You get to do it. Okay? Take this magnet, hold it like back around here. First, just hold it. You feel the vibration. That's the TV doing its thing and sending the pulse of electricity all over the place. And now, go ahead and play and move it around. Move your magnet around. People here can testify that she is changing the image on the TV. And it used to be a thing that I had to be careful. Don't put a magnet near the TV because you could totally mess it up. And if we take it on the front, I'm going to take it back. If we take it on the front, you can see if I put it like right here, I can change the image, and you can burn colors into the front of a TV if it's an old school TV by putting a strong like magnet on it. You can see I can move the electrons around right now, and I can like leave an indelible pattern on the front of the TV. But anyone else like to try to manipulate a TV with a magnet? All right, Jim, go on down. Right. If you would like to do this more, get back. Feel the vibrations. Whoa. Yeah. It's pretty cool. Sure. She's able to pull. Anybody else? All right, come on down. If you would like to do this more, the TV is here. I don't use it for anything else. Besides like moving. I'm going to put an image up there for you. Look from the side where you like around the back. Pulling that stuff totally off the screen by moving where those electrons go to. Alright. Also, one other fun way that you can observe this is if you look at the TV when I turn it off. This is an effect they still do on like Nickelodeon shows sometimes. Is if I turn the TV off, see how it condenses down to like a splotch of light in the middle and then goes away? That's the beam of electrons that is normally spread out by little electrical charges. The electrical charges on the side turn off, but the beam of electrons, the cathode ray tube, still keeps coming. And so you see in the middle of the TV, whoop, it goes to that one like piece of light. So again, in Nickelodeon, sometimes they'll like collapse the image in. That used to happen on older TVs when the magnets around the side would turn off. the beam of electrons would just focus in one spot in the middle. That's a little like clue of like what happens inside a TV. A TV is a J.J. Thomson cathode ray tube. Okay. Here they are again. Tube, cathode, electron gun. Pew! Electrons getting bent up and down by focusing and accelerating anodes and deflecting magnets to then hit the screen and make the little bits of light. J.J. Thomson took this knowledge that electrons were smaller than atoms. So that means he has to figure out how the electron is inside the atom. So he's like, all right, here's the atom, and here's one electron, and maybe there's another one over here, and some more, and another one. And he has these just chunks of electrons floating around. But electrons have what kind of charge? Negative. Atoms are neutral. So in order to balance those off, he has to fill the rest of the atom with positive charge stuff. What stuff is it? He's not really sure. So it's positive goop and negative electron chunks. Back in the 1890s in England, the delicious dessert product that everyone was aware of that was chunky bits of stuff floating in goop was, of course, plum pudding. Oh, want to pop over for some delicious plum pudding? Righto. But of course, nobody eats plum pudding anymore, so that's not really a useful model, but it's still named this in textbooks and things like that, so I have to teach you that. I think of it more, when I look at this, I think of a dessert everyone knows, I think that looks like a chocolate chip cookie. Chocolate chip cookie. So, if I had discovered it, I would have called it the chocolate chip cookie model, but unfortunately it was discovered 128 years ago by somebody else. Darn it. So now we have to call it the plum pudding model. But you should know that was like J.J. Thomson's model of the atom. Some things in science are discovered like very intentionally, where they were like trying to figure out what the electron was like. Some things in science are discovered a little more like randomly or weirdly. Penicillin is a famous example of where people were just like cleaning up for the weekend. They're just like putting some stuff in the drawer and going home for like go out and go to the bar, have a beer. When they came back in on Monday, they're like, all right, let's keep going with the experiment. Let's take the stuff out of the drawer. And they took out like some of the petri dishes, and some of them had mold on them, but some of them didn't. And they're like, why do these things not have mold on them? Oh, that stuff is producing some chemical that's killing the bacteria, killing the mold, and that's where we got this like life-saving penicillin from. The next step in science is sort of the same thing. They had a photographic plate, and they had some chunks of different minerals and rocks and stuff. And they put those two things in a drawer and went home for the weekend. Then they came back in on Monday to look at the stuff that's in the drawer. And when they took the rock samples out, they took the piece of paper out, and all of a sudden it had the image of the sample on the piece of paper, as if by magic. Okay? And so they said, what normally makes a photographic plate develop? Light. Was this thing emitting any light? No. Was there light coming in inside this drawer over the weekend? No. But there's something inside this rock that's giving off some sort of sun-like energy. There's some new energy source inside the rocks. What have they accidentally discovered? Radiation. Oh, that's the plum pudding model. In around 1900, a guy named Henry Becquerel makes the first accidental discovery of radiation. They have no idea what it is. They just know there's some new like energy sort of thing in this rock, in these chunks of rocks. They get more of this rock, and they do these crazy things where there's like, famously, one guy had a piece of the rock, pitch blende it was called, and he put a piece of it in his pocket to like take it to study later. And he got home and he forgot about it. And he took off his pants. He's like, oh, that left some sort of like a sunburn on my leg. Like, not only does it cause photographic plates to develop, but it can like create a red area. And he's like, oh, that's remarkable. And he went the next day and they taped chunks of radioactive stuff to their arm. And like, 10 minutes? No. 20 minutes. By Jove, we've got it. Like, they were like trying to like do this. They had no idea of the like other health consequences of what this stuff was going to do. One of the amazing things they learned to do back then was to put the photographic plate and put things of potential between it. This is the first ever picture of something with x-rays. That was a cross that they had. It just had a metal like crucifix cross thing. They put it on there. Here's a more famous picture of his wife's hand before they had any idea of like the dangers of exposing themselves to radiation. There are a pair of scientists, one really in particular, who's famous for their work with radioactivity, and that is this person. Who is this? Marie Curie. You guys know some of the Marie Curie story, probably. Marie Curie was from where? That's right, Poland, where women were not allowed to do scientific research. They weren't allowed into the university, even if they were really smart. And so she moved to France. You're pretty right. She moved to France to be able to go to university, to be in a sort of progressive, more liberal country that would let her like pursue her doctorate. It was an exciting time around 1900 of doing science research. She met and married a physicist named Pierre Curie. They had a couple of kids, and she was interested in this new radioactive stuff of separating and isolating the radioactive part. There was something in that rock that was radioactive. And it wasn't the silicon, and it wasn't the oxygen, it wasn't the aluminum, and the other things that are normally in rock. It was something else. She spent years studying with huge piles of this rock to get down to a few grams of the actual like radioactive stuff. One of the things that you get when you discover a new element is you get to name it. So we have things like francium and radium. She discovered two elements. She got tremendous radiation exposure. She actually died because of the radioactivity. You can't open her notebooks today. Like they have her notebooks in a sealed like safe. Like if you look at the original historical document, you need to be wearing a lead suit because it's still like so radioactive today. Interestingly, her husband Pierre sort of died because of the scientific research they did, but not as directly. He was fascinated by these new discoveries, was reading a scientific book, walking to work, and stepped in front of a bus and was killed. True story. He was just absorbed. He's an absent-minded physicist. He just like stepped in front of a bus and was killed. But Marie Curie finds radioactive stuff. Is mainly the like thing that you're known for. First person, only person to win 2 Nobel Prizes. All right. Next person we're going to talk about is Ernest Rutherford. Okay. So Ernest comes from New Zealand. When you think of New Zealand, what's something you associate with New Zealand? Kangaroos? Almost. That's right. Wolverines. I know that's Canada. Lord of the Rings. Yes. Okay. Lord of the Rings was filmed there. What else happens in New Zealand? Rugby. True. Sheep farming. Mountains. Emptiness. Okay. Do you think of like universities and knowledge and research? No. So Ernest Rutherford was a really smart kid, and he wanted to go to university, but it's far away and expensive to go to university. They had a scholarship by which you could win a scholarship to go and study in England. Ernest Rutherford got second place in the scholarship and wasn't going to be able to go, but the first place person fell in love. And he was like 18 years old. He got a full ride to Oxford, but he decided not to go and stay and become a New Zealand sheep farmer, and that allowed Ernest to go instead and run around. And Ernest Rutherford turned out to be really smart. You wonder what that other person could have done. You know, like if Ernest Rutherford won a Nobel Prize, but that person won like 3, and they're smarter than Ernest Rutherford, as judged by that one scholarship competition. Ernest Rutherford is also going to study radiation, okay? And we're going to draw a diagram of his, like, apparatus. This is a block of lead. Lead, they discovered, absorbs radiation. If I have a chunk of radioactive stuff and I put it in there, the beams of radiation are going to get absorbed almost every which way except if they go out through this narrow hole. Right? So you got that narrow little skinny thing that you can get a nice beam. The radiation itself does not glow. In The Simpsons and in popular culture, radioactive stuff is always glowing. If it was glowing, it wouldn't have taken to the 1900s for them to discover it. It would have been like in the 1400s, like, hey, look at that glowing rock. You know, like, that would not have been a hard science to come up with. All right, so it doesn't always glow. Only if you get it like super duper concentrated, which only happens in modern research, like in nuclear power plants. In order to see it, you need a screen. Just like we do with the TV, like where the beam hits the screen, it glows. That little beam right there. What Ernest Rutherford did was kind of like what J.J. Thomson does. He puts a positive charge and a negative charge above and below the beam of radiation. You should be drawing this into your notes. Okay. When he does that, they notice 2 more dots appear on the screen. 1 dot way up here and 1 dot down there. So now we have 3 things that come off of radioactive stuff instead of just 1 stuff that is radioactive. What can you conclude about this stuff down here based on the data that's on the screen? This dot here has to have what kind of charge? Not neutral. Why positive? Because it goes to the negative. Instead of going straight, again, you can't see it, but instead of going straight, this stuff gets tweaked down. It gets pulled down. So that means it's attracted towards the negative. If it's attracted to negative, that means it is positive. So we can conclude that this stuff must be positive. What can we conclude about that one up there? Negative. Because that one gets tweaked up towards the positive. It's attracted to positive. That itself must be negative. There's another conclusion we can make. Which one of the, let's say this, what's the stuff in the middle got to be like? Neutral. If I stand here, I'm just blowing, and someone throws like a ping pong ball, I can deflect it a little bit. If a gnat or mosquito flies by, I can deflect it a lot. If a truck drives by, like it doesn't care if I'm, like it doesn't, the truck is just going to keep going. Okay. Which one of these is heaviest? The neutron isn't deflected at all. It's impervious to the way we're tweaking things. Which one of these is deflected more, the negative or the positive? So which one is heavier? Positive. They conclude that the positive is heavier and the negative is light. We don't have any data on the neutral because we're not able to like touch it because it's neutral. We can't tweak it. Turns out it's very light as well, functioning massless. What is very light and negatively charged? Electrons. This stuff up here is electrons. Ernest Rutherford names these 3 types of radiation. The positive stuff he calls alpha. Okay. Oops, that's not an alpha, Dave. Whoop. Alpha. Again, it's a plus charge, happens to be +2, and it's heavy. Okay, we're going to add one more fact about it. The negative stuff is beta. It has a -1 charge, and it's light. And the third one is gamma. I'm preparing you for college right now, so you know how to go to frat parties. Okay. Gamma, that has, it's neutral, and it has no mass. As we just discovered, this one here is an electron. This is a helium atom, as it turns out later on. And this is like light energy. This is a photon. These are 3 types of radiation. Ernest Rutherford wins a Nobel Prize for these insights. If someone was sending a stream of alpha radiation at you, what do you think you could do to protect yourself? Run away might work. You could also deflect it with a piece of paper because it's just a stream of solid-like particles. And so therefore, alpha has very low penetrating ability. Can electricity get through a piece of paper? Yes. It has enough penetrating ability to go maybe like a centimeter into your skin. Gamma, oops, there's Rutherford's experiment again. Oh, there's a professional artist version of Rutherford's experiment. Here is this slide on penetrating ability. Alpha can't get through anything. Beta can get pretty far into stuff. Gamma can get totally through things. Gamma radiation is like your cell phone signal. Eventually can stop by enough concrete and lead. When you're in the basement here, you can't get a good signal. But most of the time, gamma radiation can get through things. Ernest Rutherford picked alpha, beta, and gamma because those are the first letters of the Greek alphabet, and they wanted new symbols for this new type of radiation. By the way, why is an alphabet called an alphabet? Because those were the first 2 letters of the Greek alphabet. That's where that word comes from. It's like putting things in alpha, beta order is using the Greek first 2 letters, which is pretty cool. Ernest Rutherford gets a Nobel Prize in 1908 for this, and then he makes the big discovery of his scientific career. It's kind of crazy that Ernest Rutherford is known for the thing that didn't necessarily win him the Nobel Prize. This he got a Nobel Prize for. He did more important research later on. My wife is very liberal and progressive and doesn't like to buy our son toys of war and death. But he's a boy, and when we give him rice cakes, he will chew these hippie rice cakes of his into the shape of a gun and then say pew 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 at his friends with this leftover rice cake. Boys just have this urge to make guns out of things. They find sticks in the woods. It's either a sword if it's straight or it's a gun if it has any kind of handle. Ernest Rutherford is doing the same thing with radiation. He's turning it into these little guns. So, we're going to make another drawing of a lead block with a chunk of radiation to see another experiment that Ernest Rutherford did. So once again, we have a lead block. We have a chunk of radiation, which is not green, but we just always draw it that way because of the Simpsons. And the beam of radiation coming out of it. Okay. Ernest Rutherford had a new assistant, a guy named Hans from Germany, that was coming on to his lab. Hans' last name was Geiger. What did Hans make later on in life? Famous? No. His first name was Hans. His last name was Geiger.
Oh, the Geiger scale or whatever.
The what?
That's right, the Geiger counter, which is what we use to measure radioactive stuff. So, what Hans Geiger's first experiment for Ernest Rutherford was going to do was put a thin piece of gold foil in front of a beam of radiation. And they said, this is probably just going to blow right through that very thin piece of gold foil. We just want to test your first time out observation of this. And as they expected, most of the radiation came right through. Okay? And hit that spot right there. But what was interesting was that some of the radiation didn't go and hit that spot. Some bits of it hit over here, and over there, and over there. And Geiger said, that's interesting. I'm going to put a screen around this thing on the side over here and see how wide of a deflection, sort of like an overhead view down in, how wide of a deflection could it do? And to their surprise, bleep, like it bounced out. Again, most of it is going through. Like most of it is hitting that one spot there. That's the sound of radiation hitting the screen. But occasionally, it's like going other places. And so they say, I will. They say, wow, is it going like even all the way out to the side? And they bring more screens down to the lab. And sure enough, it's going there. But it's still there. It's still hitting there as well. Right? And they say, is it even going to be behind? They're shooting what they said in their own mind was bullets at tissue paper. And the fact that most of the bullets were going through the tissue paper was not surprising. The fact that sometimes the tissue paper was causing the bullets to ricochet, that's crazy. Like, I don't want to use that toilet paper. You know, like, that's some strong stuff. Okay? And so, therefore, these little, like, flecks that are bouncing off, that's what the news is. And the news was that something in this was causing the stuff to deflect at wild angles. And it wasn't very frequently. It was like 1 out of every 8,000 bits of radiation was getting bounced off. 1 out of every 8,000 was bouncing off. Put that into your little like diagram and notes because that's an important piece of the puzzle here. So there's something in the atom that's small and causing these deflections. What is our current model of the atom?
Circle.
No, we got past that.
Oh.
A chocolate chip cookie. And it's got goop and it's got electrons. And the electrons themselves, they're pretty small and useless. So it's weird that there's something in the atom that is doing this. What does Rutherford propose is in the nucleus that is small and hard and able to deflect these bits of radiation? We're not there yet. You guys are a step ahead. Rutherford proposes a nucleus. The idea that there is an atomic nucleus, this is the first experimental evidence thereof. This idea that you have an atom, he was the first person to come up with this and say there's a nucleus. I think there's an E there between the C and the L, but I don't really know because I can't spell. Here is a professional artist rendering of these things. If the Thomson model had been correct, all the radiation should have been able to blow through that thing. But because the Rutherford's model is correct, things were bouncing off. Right? There was something in there that could cause radiation to occasionally deflect. Here is also a professional artist version of that gold foil experiment if my diagram made no sense to you. Right? Here's the radioactive source, beam here. Sometimes it gets deflected. Most of the time it goes through, occasional like deflections. This is not true because they didn't originally set the thing up all the way around. My like telling the screens around it is a more like honest story of how it got there. We're going to draw an atom. We're going to try and represent this net data. If, like Trace, you've got a pretty significant part of your page still available, great. Draw as big a circle as you can on that page. Yeah. If, like Teddy, you've only got a few lines, you're going to go to the next page. You're going to draw a big a circle as you can on a piece of paper. Go. Draw as big a circle as you can on a piece of paper. Draw as big as you can. Okay. I am going to draw as big as I can on there. And now I'm going to put a dot in the center of your piece of paper. No way. Pen is off. That's what we want there. Okay. Why am I belaboring this point and making her draw an enormous circle on her piece of paper? Because we are trying to accurately scale and have a real picture of an atom. And when we do that, if we think about the dot that I made there and the dot that you just made on your piece of paper, how big is that dot relative to your atom? I'm going to make some more dots. I'm going to make 1, 2, 3, 4 more dots. That's 5 dots that size, more or less. You don't have to make 5 dots. Just draw your circle and your dot. Okay? That's 5 dots. Those 5 dots are about the width of my thumb. So if I do another thumb, come on, sparkboard work. Okay. Smart boy. All right. So if I do another 5 dots worth and another 5 dots worth, that's like 15, 20 dots. Maybe that's a little bit big. I'll say like this is about 20 dots. So therefore this is like 80 dots, 100 dots. Is that right? 20, 40, 60, 80, maybe 100 dots. If I were to draw 100 dots, that would be the width of this thing. So this dot, that green dot there, is about 1/100th of the right side of the atom. What fraction of the atom should it be? I gave you a particular number. 1/8000th. So how many times too big is that green dot for this picture? 80. That green dot is 80 times bigger than it's supposed to be. I can't draw on my smartboard a good enough picture to show you how small the nucleus actually is. So on your whole sheet of paper with a circle and a dot, you should label that dot too big. The real nucleus is actually smaller than you can draw if you're putting a dot on an 8.5 by 11 sheet of paper. Okay? This is exaggerated for scale, which is crazy because in most scientific textbooks, they draw like this. This nucleus is like 1/4 of the atom, and really, it's like 1/8000th. In order to make it visible, so like kids can be like, oh, I see in the picture, they always draw these nucleuses that are like way too big. Okay? So if you have the nucleus, no, they're smaller. If an atom was the size of a soccer field, or frisbee field if you prefer, if the atom was the size of an athletic field, the nucleus would be about the size of a penny or a dime. If you think about a grass field, like showing up for soccer practice and be like, oh, I dropped my dime at some point in practice today. Can you guys help me find it? I'm like, no, I cannot see your dime out on this field. Right? It's going to be lost. Right? It is so small. If you're seeing the whole field, if you're like, go up in the bleachers and look and see if you see my dime on the field, like, you're not going to be able to see the dime on the field. It's going to be too small. And then they're like, but what about the electrons? The electrons are the same size as FDR's eye is on the dime. If you look at the dime, it's got Franklin Delano Roosevelt on it. If you look at his eyeball, that's how big the electron is. So if you have a carbon atom, carbon has 6 of those electrons. Those electrons are the size of like gnats. So in an atom, it's like thinking about a football stadium. Like, oh, I'm at Debbie now, I'm up in the stands, and there's a dime on the football field, and there's 6 gnats moving around. And that's all there is. And what is the rest of matter? Nope. It's empty space. There is nothing there. And it's, I think, reasonable when we think about atoms. We can be like, okay, the atom is mostly empty space. But guess what? You're made of atoms. And if you look at your hand is mostly empty space. And so the table and your hand, you should be able to put your hand into the table because it's empty and you're empty, but you can't. Okay? Okay, let me try one more time. No, I can't. Okay? Why can't we? Last thought. Why can't we? Because those electrons, those gnats, are moving at almost like 1/10 the speed of light. They're moving super fast. And so are the gnats in the table. And so, although most of the time it's empty, they find each other and bump into each other and repel each other and push off each other, and that's what keeps you from like falling into the table. Right? You are empty space, but you're empty space that's moving, and so it ends up occupying space. Raise your hand if you do not own some sort of earbud or skull candy or listening technology. Okay? Everyone has that something. I want you to bring that to class on Friday. I want you to bring earbuds. I also want you to bring you this homework, which I'm about to hand out to you. Make one pass down. Thank you for your positive energy. Alright. So, each scientist we have talked about is a vertical column. I have done Aristotle as an example for you here.